That was going through me at a similar voltage. Huh. I didn't glow though. In order to counter the atrocities in Mextraf's video, which had 600,000 views in the past week, and he has somewhere around 171,000 subscribers. So that's a lot of people that have seen this rather dangerous project where you're connecting yourself to the mains in order to test some LEDs. And that's not very good. So I've come up with the idea to power it from batteries instead, using a CCFL inverter that you can find in any scanner or other old equipment. You can also find CCFL inverters from those neon strips that you could get for computer cases and other purposes like that. But yes, this can apparently run 2 tubes, but you only need to use just you just remove one of the capacitors. Okay, so in this recent video by Mextraf, we can basically reverse engineer the light bulb's inverter. It would nearly always be a boost converter of some kind, so long story short with that, the positive connection pretty much comes straight from live neutral, and the negative path of the output is also connected straight to neutral by the switching transistor and inductor. So at any given point on the output, there is nary any protection between the load, or you being connected to the load, and a live or neutral grid connection. You're connected to that, and if you come across ground, you're going to pass pretty much all the current to ground, which is what makes this circuit exceptionally scary. Is not just the fact that it's another dodgy YouTube circuit of how to make this thing that's connected to the mains that you are going to be playing around with, or otherwise produces dangerous voltages that you're going to play around with. This one is designed to test LEDs, Zener diodes, any electronic component that has you want to measure the voltage drop of that, and so you're going to be playing around both probes in hand. This guy showed our croc clips in hand, poor insulation. So if you've got 100 volts in both hands and those things, you're going to get a shock off it, inevitably. In the video, you could see his croc clips are also melted and charred and stuff, so they've been through hell and back, and at that point, they're not an insulator anymore. So what I've done is basically rectify the output and smooth it with a 10 nanofarad capacitor. Mind you, the frequency in here is in the tens to hundreds of kilohertz, so that's more than suitable, especially when you have such a low current, typically only a milliamp or less. And then you have the neon here with its resistor that kind of acts as a regulator. You'll see that characteristic in a moment when I power it up. Ideally, you want to have 2 100k resistors, one on both pole. Otherwise, yeah, if you leave just one connected, it's good practice to have one on both, so that you can't have a low impedance path. Common thing that they'll do, yep, they have done it here as well. You'll see that on the high voltage output side, there's the capacitor and the output plug. It's all isolated and well. But then you got the negative, or quote ground side of that CCFL tube. That trace is running up to the ground plane of the low voltage side. It was wired up that way in one of the converters I was handling, and as I was unplugging it from the low voltage side, I must have come in contact with something around here, and, well, completed the circuit, got a nasty shock. Which probably wouldn't have happened had the low voltage ground not been part of the high voltage ground. Which is why I rather fancy these devices, because they didn't do that. They didn't connect the they did not connect the ground of the output to the ground of the input. Yes, that might have EMI problems, but you could fix it by slapping one of those capacitors across the 2 grounds. So you have a nice isolated output with some of these, not all of these, but some of these, you can get a decent isolated output. And in all cases that you try to use one of these, you want to have a resistor on both positive and negative, so that whatever you're finagling with out here, if you touch both of those, you're not going to ever have any risk of a full whack, especially if this is mounted in some kind of grounded enclosure or system that you may be in contact with somehow. One single sad LED in there that's working. Turn it around. Common mistake. Chuck it in backwards. Ooh. Ooh. Backwards LED. What happens when I put it in backwards like that? Does it still work in the forwards range? Blinking and not starting. So, yeah, it's the instantly pop your LEDs, you put it in reverse. This is not for measuring LEDs, even though it's made to measure LEDs, which is absolutely stupid. But yeah, unless you've got the appropriate reverse protection diode in there, as these LEDs do. So you can see the 0.8 volts, and then it's still fine. Well, yeah, bad connections, but yes, it's still fine when I check its output. So how can we stop this from happening? We know that these LEDs can handle the reverse, but a normal one pretty much cannot handle the reverse. So I'm going to try higher value of a resistor. So first, for this particular one, the other one worked fine based on one of these, and got some nice zings off it and everything. Probably going to get a zing off it if I touched any of this, but hopefully not when I'm on the other side of these resistors. I was getting a shock off it before with the original 30k or so. So here we go. Oh, yep, I've got a very faint glow coming off of this. Apparently I have 338 volts here at the output, coming from 3. Yeah, let's just see if it does anything. Oh, yeah, I can feel it. I can definitely feel it. Ooh. Ooh. But I can't feel it, really. Come on. No geniuses over here, but better than absolute dingers. 117, yeah, that's working out. I measured these with a different voltage source, but that's working great. Great, mate. Great, mate. Let's check this. I can measure the glow. Oh, that's actually a nice glow. That was going through me at a similar voltage. Huh. I didn't glow though. Yeah, I'm happy with this one. Oh, would you look at that? It's not like they're dim or anything. I can't see which one's on or which one's not. Okay, yeah, I just shoved them all in reverse too, and they're all still fine. And just one. Cook them up. 7.4. It's infallible now. Yeah, 30k. 4.4 meg. Still getting the well, there is 500 volts on the whack on the other side of that thing, but yeah, let's put this in reverse, see what happens. 338 volts going down to 200. That's a high blocking voltage for what, 3 LEDs in that package? .48. That's nice. It's good to know. The current in this is exceptionally low, so yeah. It's blocking 149 volts. Nice. And it's guaranteed not to be dead, I'm pretty damn sure, because the current flowing through this is like, what, microamps? We'll give that a test in a second. So, yeah, he's still fine. I think this one still works. Yeah, it still works. Just get your current reading there while I shove things in the holes and see what happens. Oh, yeah, that's actually a little bit more than 50 microamps, but yeah, I don't think 107 microamps coming out of it that's nothing. Compared to a whole 3 milliamps blasting through your fingertips, well, it's not that much in the grand scheme of things, but that is still, it's a shock risk. I think it's 5 milliamps or also is what can start vibration. In a child, I think it'll be much lower, so yeah, a kid playing around with that dingus circuit is going to get a shock, and it could, the act of being in shock from the shock could also just enhance the whole dying and electrocution side of things. So making the safe circuit from the get-go is, that's just, I thought that'd be common sense, but apparently some people don't have that much common sense. That was really only there to protect this power supply in the end, although there would indeed be two of them, one on each terminal. In this case, there is one on each terminal, and even though this has a kind of live ground in it, technically it is all, once it was potted or assembled in the final enclosure, you make it so that only the wire on the outside of this, everything's on the other side of these high value resistors, 2.2 meg, and if you really want to feel safe, you just add another 2, so you have 4 of those things in series, effectively. So, and in that case, I'm pretty sure you have your 60 microamps. 50, actually. That seemed like it was pretty swollen. So I'm just going to continue playing around with that one, because that was cool. I'm going to check back at his tray, actually. Yeah, so you can test mobs. That's a good thing to do. If I had more voltages, it looks like that my 10 mega ohms of resistance of this is actually loading this down a bit. So there's a caveat there. But it's this is way more than anticipated. This is really good. I have a lot of fun with this. Yeah, here's what's left of the the light bulb. Yeah, I had some fun with trying to get that out of its base, and it didn't come out, so this is one of the ones that I've used here. It's 7N471K. Very, very common metal oxide resistor. You'll find them in most power supplies that have actually included the mobs on the supply. I'll zoom in so you can see those part numbers. In fact, I'm pretty sure all of these mobs would be suitable, apart from them. There's another one here. That one says 220. Let's give it a test. Yes, it is 220. Alright. So that one wouldn't be really suitable. You notice that at the end it says, oh yeah, we're all in the dark here. So you notice it says 471 at the end. That would be 470 volts. This one would be 560. This one apparently is 250, but it didn't measure out as such when I put my meter on it. Zoom back out for the meter here. Yeah, so it's that 328, 300. So I think this is more like a VDR, and these are mobs, but I don't know, they're all kind of the same-ish. But yeah, you got 221 here, 14221 here. check these in there. We actually do get 221, 223, 248, going all over the place because the resistance, but that's interesting. Yeah, the series resistance actually does make a difference. The contact resistance at these voltages actually makes a difference. I didn't think it would, but yes, 471 is 471 is what we've used for the MOV in our circuit. And as you can see, I've got a collection of metal oxide resistors here. And then yeah, there's these vintage devices actually. If I can get one out. Well, yeah, that's this thing that I was testing over here. With the 775. I'm not too sure what they're right thing, but I know that K75, it's supposed to be 75 volts, but that's probably thresholds. Its actual trigger and clamp is at 120 volts, but it's a bit higher than this interesting little rating there. I guess it's meant to protect a 75 volt rail by allowing it to swing up to 120. So that's why it was useful to write that number down for all these particular devices. I wish I got a fair few. So MOV measurements to go. The neons and stuff, although the neons came out with lower voltages. But realistically, well, that's just going to line it up and show 67 volts, 54. Yeah. 8.2 volts exactly. So this little guy is actually spot on, even with the 100 microamps of current here. I have a little bag of Zener diode. I'm pretty sure these are Zeners. They've got stripes all over them. So it looks like they form to a color code. Let me just check it. 0.65. And 1.8. It might actually be a bit higher, but yeah, that's interesting there. Now this one, 0.65. 23. 23 volts. So yes, there's definitely a Zener diode. Nice to be able to identify parts so rapidly. And the fact that those are the only two Zeners there, that all the rest of these are normal. Which is good to know. See what these are. 13. Of course, they're all just diodes on the other side. Are these supposed to be? Yes, they are. 13 volt. No, it says 13B3. 13 volt Zener though. Try these ones. They're all just going to be diodes. Four point two. 4.3, 4.6, 4.3. Are they all supposed to be 4.6? No, they're supposed to be 5.6. Oh, that's a little bit under then. 4.6. So yeah, some of them are off, but That's typically on the low voltage ones. Use a different tester to test those for finite measurements, but for checking whether it's a Zener diode or a 1N4148, this is perfect. Is this getting hot? I'd hope not. Well, it is hot, but I hope not fire hot. Measuring 5.3, 5.2. That's interesting, because these are also oh, that's interesting, because these are also 5.6 B3, and these ones are also, no, these are 5.6 B1, okay, so they're different. Not much more I can really add to that, because it's self-explanatory. Measured Zener diode, measured MOV, measured the LEDs and chucked them in reverse and they didn't pop. I think I can put something else in front of this. In reverse, so I should get a diode. There you go, there's our diode. Now, let's test this thing's forward blocking voltage. 9.5. At that current. Actually, we didn't do one thing that usually you're supposed to do with that. You do that. Just crudely shorting the base to the ground. Blocking voltages now not in focus, because the phone's a freaking idiot and decided, focus on the wire, it's in my face, so it must be the topper. No, it's not. The MOSFET's the topic. There, with it shorted to ground and assured to be off, the blocking voltage is 64 volts. Otherwise, with a floating gauge, it's like 5 volts here now. I could have just cooked all of this too, but probably did actually cook all of it. Okay, 26 now. It must have picked up a charge from touching it. And now it's off fully. So, variable blocking voltage there. With when the pins are floating. Because you don't know what the gate charge is. It could be anything from 0 to it breaking down, or I don't know. Anything, really. But when it's guaranteed off, guaranteed 64 volt block. Okay, that's good. Hey, learned something about this MOSFET. I can do that with transistors and every other device under the sun. Apparently even LEDs without frying them. This thing in the way, as usual. LED. Oh. What's your reverse blocking voltage? We all want to know. Why is it so high? It's at 65 volts in reverse. And it's just an LED again. I think it's a little bit dimmer, but I don't know. And yeah, I'm going to be replacing them all at some point. But yeah, it's still working pretty much fine. It might be a bit dimmer, I'm not sure. But yes, it doesn't cook them instantly as the other one does. This one's just cooked instantly, it's already... Yeah, it's fine. Okay. So now I'm going to measure the approximate current draw of this device. Right here, make contact. 14 milliamps. Turn it to the 10 amp range, it might, which will be better. Oh no, 16 milliamps. I still can't get over the state of the alligator clips in his video. And also just poking and prodding the output, like, oh yeah, that's going to be fine. I know for a fact that it's not fine. Unless, of course, yeah, I just turn it off and, like, conveniently, oh yeah, I could just touch it all over. That's the part that he doesn't show, is that it was off when he did that. Else it'd be a little bit more like, I have to do it now. I have to do that. Oh, a bit more like that. Back and, oh, I can feel that all up my arm and everything.